In this lesson, you will learn to recognize and name convex, concave, and regular polygons, as well as how to find the measures of interior angles and exterior angles of convex polygons. Now, in our objective, there are a lot of terms that you do not know at this point, and so we're going to begin by going through our definitions. So the first word is the word polygon. What is a polygon? Well, you see the word polygon is made up of two parts. You have poly, and then you have gon. The prefix poly means many, and then gon is Latin for angle. So polygon literally means many angles. Now this might not be too helpful for us still, so let's now describe polygons. What does it mean by many angles? Well, the first part of our description is that it has straight sides. Polygons also are going to be closed, and it does not cross over itself. So here are examples of polygons. We see that we have straight edges. We see also that it does not cross over itself. And we see also that it is closed for each of these three polygons. Whereas here, these would not be polygons. The first one is not a polygon because it has this curve around the side. Second one is not a polygon because it crosses over itself. And the third one is not a polygon because it is not closed. There's a gap right here. Now with polygons, there are different types of polygons. So the first type is a convex polygon, which by definition says that no line containing a side of the polygon contains a point in the interior of the polygon. That's kind of still difficult to understand, so let's contrast convex polygon with something that's not convex, and that would be what we call a concave polygon. A concave polygon is the opposite, and the picture of a concave polygon would be as follows. So notice the difference. Concave polygon, it kind of caves in. So right here we see this point is inside or in the interior of the polygon, whereas the convex polygon does not have a point on the inside like that. So the convex and concave polygons are opposite of each other. So think of concave, you have the word cave in there, and it looks kind of like the mouth of a cave with a concave polygon. In addition to convex and concave polygons, we can also name polygons based off the number of sides. So a three-sided polygon is what we call a triangle, and we've discussed that already. Four-sided polygon we would call a quadrilateral. The prefix quad means four. A five-sided polygon is called a pentagon. Six-sided polygon is called a hexagon. 7 sides we call a heptagon. 8 sides is an octagon. 9 is a nonagon. 10 is a decagon. 11 we call a hendecagon. And 12 is called a dodecagon. So all of these prefixes at the beginning of the word kind of signify the number of sides, where penta means 5, hex means 6, hepta means 7, octa is 8, and etc. So to help you visualize each of these, here's a picture of the different types of polygons. Here's a quadrilateral having 4 sides, pentagon has 5 sides, hexagon 6, heptagon 7, and etc. Now let's discuss how to name polygons. Here's a polygon with the vertices of P, C, H, I, and M. And to name the polygon, what you do is you list the consecutive vertices in order. So for example, if I start with the letter C, then the next letter is going to be an H, and then the next letter is going to be an I, and then M, and then P. So we can call this polygon CHIMP, or polygon chimp. And it does not matter which letter we start with. We can start with any letter, and we can go either direction, either clockwise or counterclockwise. So we could also call this polygon HIMPC, where I start at the H instead, and then go to I, then M, then P, and then over to C. Or you can also call it polygon CPMIH, where I'm starting with the C, and now I'm going counterclockwise instead. So I have C, then P, and then M, and then I, and then H. So it does not matter which letter I start with or which direction I go, as long as we are going in order. So there are multiple ways that we can write this. What would not work would be something like C, and then H, and then jumping over to the P, and then doing maybe I and M. Okay, this is not in order, so this would not be okay. Next, we have a term that you need to know, and that term is the word diagonal. And a diagonal, by definition, is a segment joining two non-consecutive vertices. So for example, here, looking at the quadrilateral has four sides. If I were to draw a line from this vertex across to this other vertex, this red line would be a diagonal. And what we were trying to do with the diagonals in this slide is we are trying to determine the interior angle measure. So if you add up all of the angles inside of the different polygons, what would they add up to be? So looking at the quadrilateral, there are four sides. If I draw one diagonal, notice we have two triangles inside of the quadrilateral. So we have two triangles, and we've learned before that a triangle has 180 degrees. So we have two triangles, so 2 times 180 would give you the angle sum. So if you add up all of the angles inside of this quadrilateral, you would have 2 times 180, or 360 degrees. For the pentagon, there are 5 sides, and if you were to draw diagonals from this vertex to the other vertices, you would have these two diagonals. Notice we now have 3 triangles. So if we have 3 triangles, and each triangle is 180 degrees, the total angle measure inside of the pentagon would be 3 times 180. With a hexagon, we have 6 sides, and if we draw a diagonal from this vertex to all the other vertices, then notice now you would have 4 triangles. So if you add up all the angles inside of the hexagon, we would have 4 times 180. And then heptagon, we have 7 sides, and then if you were to draw the different diagonals going to the other vertices, notice we have 5 triangles, and so the angle sum would be 5 times 180. And this can be extended to any number of sides in the polygon. So not only for 4, 5, 6, or 7 sides, but it could be for 8, 9, 10, or 100 sides. And our objective here is to see a pattern so that we can find the angle sum just by knowing the number of sides. So notice, if we have 4 sides, we have 2 triangles. 5 sides, 3 triangles. 6 sides, 4 triangles. 7 sides, 5 triangles. The number of triangles that are created will be 2 less than the number of sides that we have. So if I take the number of sides, we'll call that n, and then subtract 2, we have the number of triangles. So n minus 2 is the number of triangles, then multiply that by 180 to get the interior angle measure. So what this does for me is now it allows me to use this little formula to find the sum of the interior angles for any type of polygon, whether it be 4, 5, 6, 7 sides, or it could be 100 sides. So using the same polygons, let me show you how to use the formula. So the formula is n minus 2 times 180, and for n, we're going to plug in the number of sides. So quadrilateral has 4 sides, so we have 4 minus 2 times 180, which would give me 360. Pentagon has 5 sides, so we have 5 minus 2 times 180, which is going to be 540. Hexagon has 6 sides, so we have 6 minus 2 times 180, which gives me 720. And a heptagon has 7 sides, so we have 7 minus 2 times 180, which gives me 900. So all we do for finding the sum of the interior angle measure is we plug in the number of sides in for n. So if we had a 100-sided polygon, we want to know the sum of the interior angle measures. We plug a 100 in for n. We have 100 minus 2 times 180. Now looking at a lot of the same shapes that we had drawn, there's another term that you need to know. And that term is the term regular polygons. A regular polygon, by definition, are polygons that are both equilateral and equiangular, meaning the side measures are all the same, and every angle inside would also be the same. And that's what you see here in all of these pictures. where we have the sides being the same and the angles are the same. Now looking back at the previous slide where I'd found the angle measure for each of these different polygons. This is the sum of the interior angles, meaning if I add up these 4 angles together, I'm going to get 360 degrees. Same thing for the other ones. If I add up all these 5 angles, I'm going to get 540, and etc. Now if we have regular polygons, meaning the angles are the same and the sides are the same, then if we wanted to find one angle, we could do that very quickly, because for a quadrilateral, we have 4 sides and 4 angles. So if we divide the total angle measure of the inside by 4, we're going to get the measure of just one angle. And that's going to be, in this case, 360 divided by 4, which gives you 90. Which makes sense, right? Because this would be a right angle, this is a right angle, as with these other 2. And same thing with a pentagon. Pentagon has 5 angles and 5 sides. If the total angle measure is 540, and I want to know just one angle, I take 540 divided by 5, and I get 108 degrees. Hexagon, same thing. I divide the total interior angle measure by 6 in this case to get 120 for one angle. Heptagon has 7 sides, so I can divide the 900 by 7 to get one angle equaling 128.6 degrees. And that concludes our lesson for today. We will see you next time.